to us physically. Entanglement is just like we can't describe the state of one particle or something that's singularly without, sorry, independent of others. So one kind of very popular visibility phrase like the action at a distance, right? And that was really cool. But you to describe it kind of mathematically, we need to talk about like how we can like combine systems, like how we can like talk about states in this combined system. The first thing is kind of what a qubit is, because this is an idea that's like a very basic like state that we have sometimes. When you think about like a classical bit, like a 0 or 1, or when you have a qubit, we want to think about combinations of these states between 0 and 1, right? And often we use this notation where we have like these kind of like little bars around, or like angle brackets around our state. And what that kind of just means is it's called it's called I think a ket. And what it means, it's a vector in a certain space, right? And we call the dual of this a bra. Later on, we'll see that sometimes we kind of just use kets as these like column vectors and bras like row vectors. That way we can kind of like multiply them out and get matrices. This kind of refers to a thing called Hilbert space. So when we talk about quantum states, we talk about a thing called Hilbert space. It's a vector space over either real numbers or the complex. We have an inner product. We like I don't think it's used to define what an inner product is. It's just a thing that takes in two elements of a vector space and gives us something in the field, and it's a generalization of the dot, where the dot product is in like R like R2 or wherever you do it, right? You might see in the future, and often often you'll see in the future when you do like quantum mechanics, but it's not really important to us here other than the fact that we have this structure on our vector space, and we're going to sometimes treat it as over C because over R is particularly like more interesting like when we look over. So we're gonna use this thing called the tensor. I'm not gonna just tell you what the tensor is because it's really complicated, but you need to think about it as just combining systems. So when we have we want to think about our vector spaces or vector spaces as systems, because inner states are the states of or vectors in those systems that kind of describe the state of the system. You know what I'm saying? So when we talk about like this tensor product, it's gonna be kind of used a lot, but without defining it, it might seem a little bit like hand wavy. And that's kind of a little bit of a point. Like I think when you do math sometimes you have to accept that you might not fully understand what's going on, but you kind of like go with the flow, like you kind of suspend disbelief, right? So when you see this, you kind of want to think about like a state in a combined system and just to try to appeal to your intuition. It's usually a good way to do it. Just try to think about it intuitively of combining our systems. And you remember that with any vectors in our original like systems, when you put them together, we do have a combined vector, a combined state in the new system. And we have like a funny term for like when we combine these, we call them like bipartite if it's two systems, or like generally n systems. And the way we're gonna kind of denote this is we're gonna have like this. We're gonna have the h like 1 dot through n. To kind of this is an n partite system. We have n different systems, subsystems we kind of put together into one big system. Often we want to go back to our intuition. If we don't know what, we can't describe the system independent of other systems. Like I think it was kind of like combined, and we can't really like separate it, so to speak. It's not separable, which kind of appeals to this idea that we can't like break it apart into like more basic things in our subsystems. Right? And this is kind of what it means to be not entangled. It's called a product state. We can break it down into these tensor products of states and subsystems, right? And this kind of makes sense. We can like describe it in simpler terms. We can kind of describe it independent of another state, right? But if we can't do this, then we have a much more complicated system where it's, in fact, we can't separate, we can't break it apart, and we have descriptions between other states, and that's the interesting part of our life. Right? It's kind of what we're looking for. And this is useful to detect because, like, oftentimes we'll have systems where we want to figure out if we can separate things, or some people want to have things be entangled, right? And just the essentially, when we think about these density matrices, often people are brought in as the common row vectors, and they describe, in a sense, like probabilities, and it's kind of think about the intuitive probabilities. We're going to focus on just on this pure state density matrix. If you care about the generic density matrix, maybe it's interesting. But for us, we kind of just care about the pure state because that's all we're really going to use, right? And we're often going to want to, like, if we have an operator which is just a mapping Hilbert space to itself, we kind of want to talk about like restrictions to certain like action on certain kind of like states, right? Or we use density matrices. Just restrict these using support projection operators. And kind of when we just think about this, if we're only working really with pure states, then we only worry about it just being the density matrix. For the generic like, mixed states, you diagonalize and you drop your lambdas, but it's not really important to us. As long as you remember that this is our density matrix, and to project onto our the action, we just apply our density matrix or restrict to our density matrix on both sides. This is all we really need to do. We don't worry too much about like the generic state or the mixed state because it's not too important for us. We're gonna like go through examples. And then so this is a bit daunting. It looks like a lot. The only thing to think about is that we're going from n particular Hilbert space to n particular Hilbert space, and we have access to the bases of these different spaces, right? Sometimes we want to restrict our operator to only work on like part of it. Well, let's say like we have like a 1, 3, like 1, 2, like Hilbert 1, 2, 3. But we just want to work on like 1, 3. The way we do this is like partial trace. So we just trace out the bases of the subsystem we're working with, and kind of just that leaves what's left. And it looks a bit daunting, but just think about like, okay, we have one that's going from type of space to n particle space. We kind of want to restrict it down to n minus 1 part type. We're just going to kind of trace out, kind of just like intuitively just think about like ignoring this subsystem that we just kind of get rid of. If you don't know what a trace is, it's just like taking the sum along a diagonal. So it's going to give you like a scalar term, so it doesn't influence the rest of our things. So when we think about like how we want to collect these, right? Sometimes like we want to think about how a operator acts on a state. We need to collect these. This is kind of how we're going to describe entangled states in a bit. We collect their operators in this thing called entanglement K-form, which for the density matrices. I forgot this part. This is notation. We just kind of get rid of the thing we traced, the subsystem we traced out, just for like our own sake, to make it like concise, kind of like crossing out or something. And then we also have this restriction operator, which just restricts the input and the output, so to speak. So it's just like always making sure that we're acting on kind of around this state, right? Because we only really care about the state. Whatever else the operator does isn't that important.
So we're kind of like thinking about it like the difference between these, like in a very hand-wavy sense. But like I wouldn't worry too much about understanding why we choose these as our operators, and just that they work. Like they work, and that's perhaps the most important thing.
Yeah. So, I guess like a much more concrete example is thinking the qubits we were talking about before. We're like a two-dimensional. So it's saying like thinking about like we just have for each of our subsystems, they're two-dimensional. So we have 0 and 1 as our basis for each one, and they just look like that, like in terms of their matrices. I guess it's that kind of. I hope that kind of makes sense. And for our combined system, we have four basis vectors, which are like 0, 0, 0, 1, 1, 0, 1, 1. Kind of like a classical computer. Right? This is, I think, kind of makes sense. And there's two very like particular states that are useful to look at, and that's
1, 0, 2. But the entangled state looks a lot more complicated. Think about if you want to separate A and B in the system, or like any of the states, it becomes really complicated because of this factor going on. In fact, it's has a special name. It's called a Bell pair, or like one of the Bell states. There's 4 of them. This is probably the most famous one. And for us, like, I think you can look at it and say that it doesn't.
I should probably swap mics.
Like this doesn't look like this second thing doesn't look very nice, right? And I guess
given its name, it's most likely entangled. But I guess you never know, right? So going back to this process, because we want to make sure that this makes sense to us. What actually is this? It's just the rows are row vector, and the columns are the column vector. So, like specifically, if you just look at the example of since the density matrix of product state, right? We're going to be multiplying 0, 0, 0, 1, 0, 2 like, by the row vector, which is like the exact same. So it's going to be a 4 by 1 and a 1 by 4, so you got 4 by 4 matrix at the end. And it looks like it's probably going to be like 1 and 0 everywhere else. You're right, like you multiply those times, 1 at the top, 0 everywhere else. Or the entangled state. It's a little more complicated because of what's going on. The end it gives us this thing, which isn't like particularly nice looking, right? And I think still like intuition tells us that maybe something goes awry here, right? And just as a note, like because they are pure state, because we only have the raw and the ket, split British offers the exact same thing, right? So so we don't have to worry about like calculating those things by diagonalizing. And specifically, what we want to do is also trace out subsystems. This is important to us, right? So tracing out the action of A, the action of B in the product state. These like they both do the exact same thing. They should be the same, right? As in the trace out, so we should have like PA is with PB. Sorry, yeah, right. The trace of the subsystem. We want to think about like if we restrict our action only to one subsystem. What happens? It just becomes this like 1, 0, 0, 0 matrix. Whereas for the entangled state, what happens is that when you take these, first you'll get a factor of 1/2 out, which is just I guess. And then you get the identity Um, maybe it's a nice thing, but maybe it's not. And I think when we apply it, I think our last few things we would put these together. So we're gonna start with a complex. So we're gonna start with a cochain complex. It goes from complex numbers, the one form and the two forms. The same way we did it in the general bipartite case. And all we're gonna do is just apply the same DMAX, which is multiplying by a scalar for the first one, right? We multiply by a scalar and we get these things. But then what happens when we use the D1 form is that we get the exact same thing with a little more complicated, but it's the exact same thing we did before. And what ends up happening is that these form particularly important because what happens is, firstly, I'm going to say this as a preface, don't worry about what these are how you get these, because these are a little more complicated to how we get them. It has to do with our free form and stuff like that. But importantly, for the product state, the kernel of the kernel and the image are persistent. The equivalence class is 0, right? So the dimension is 0. That seems right. And then for the product, for the entangled state, it's this really ugly thing. You have 6 dimensions. This thing is 6 dimensions, so our this is not clean, right? And the important thing to take away is that every time we have an entangled state, we want to make sure we have it such that the dimension of this cohomology group is greater than 0. These are non-trivial things that are in there, versus when it's a product state, they actually all end up happening that the kernel is precisely the same as the image of this map, and we have no dimension is 0, right? And that's kind of it. That's the whole gist of it. So let's see what the references. If there's any questions that anyone has? Yes. Yeah. So essentially, when you put into this cohomology group, the exactness fails, right? Or the cohomology is non-trivial. Any other questions? Yes. Yeah. Oh, what would it mean if you had maybe a longer cochain complex? It's failure of exactness on the right. That's precisely this ptosis. So specifically, you do these things called Poincare polynomials. They tell you whether how this cochain complex looks. But as long as there's a failure of exactness on the right, it just tells you that there's a entangled state. I don't know if there's any physical significance to specifically the dimensions or anywhere else that it might fail. Maybe there is, but this is something we don't know. This is something that's, I guess, if you're interested in it, look into it. Maybe it's a new thing you can do. But that's kind of all we know. The failure exactness on the right is kind of what we're looking for. What we're looking for if we want to find an entangled state. Yeah. Any other questions? Yes. I mean, this is not. I know it's not. They might, but as far as I know, for these specific things where we use coaching complexes in the forms, there is another kind of complex. This is it's Mainiero's paper. They describe these first. There's 2 kinds. There's the GNS and the commuton. This is the commuton complex I mentioned before. I think the GNS complex might have a little more to do with it, but still, cohomology is the main thing. But whenever, I don't know physically why, just mathematically it was to be cohomology rather than homology group. It's interesting because I don't know where else the homology ends up in Yeah. Yes, maybe if you take like, yeah, so maybe if you take vector rules, like you'll get homology back out. It's just like if you take, like that might just be the same thing where you just take the dual of a vector and just work on that instead. You'll probably just get the dual of cohomology out. But I guess the physical significance isn't like any different. Like we're just telling ourselves the same thing, right? With operators restricted to the rejection operator. Oh yeah, you're right. I'm trying to think. I don't know what, because I don't know if this is I don't know. Maybe there's some kind of, because for me, like my first thought is like maybe this is like just like me mathematical, but I want to take like opposite categories and see if there's any kind of significance there. But like I don't know off the top of my head if there's any kind of interesting thing going on. Because if you take like what we're doing right now and just go in like the opposite category or errors are reversed, we'll just get like the homology back out. But like this is not a really useful statement. We're just turning around the arrows and we're just saying like same thing. Uh,